Hello everyone, today I'll be reviewing a fascinating research paper titled Degradation Model based on Tsai-Hill factors to model the progressive failure of fiber metal laminates, written by M.V. Rao and V.V. Subba and published in the Journal of Composite Materials in 2010. This paper explores how we can better understand and predict the failure behavior of fiber metal laminates, often called FMLS. These are hybrid materials made by alternating thin metal sheets with layers of fiber reinforced composites, such as glass epoxy. You'll find them in modern aircraft, spacecraft, and other high-performance structures, mainly because they are strong, lightweight, and resistant to fatigue, corrosion, and impact. But as advanced as these materials are, modeling their failure behavior is extremely complicated. When FMLS are loaded, they don't simply break. Instead, they go through a series of gradual damage events. Things like matrix cracking, fiber matrix debonding, fiber failure, and even plastic deformation in the metal layers. Capturing all these interacting failure mechanisms in one model is a real challenge. That's the main problem these papers aim to solve. Traditionally, researchers have used classical analytical methods to predict composite failure methods such as Tsai-Hill or Tsai-Hill criteria. These work reasonably well for single composite laminates under simple loading, but for fiber metal laminates, which include ductile materials and multiple interacting damage modes, these traditional models fall short. Earlier, degradation models often assume that once a layer fails, its stiffness instantly drops by a fixed percentage, say 50% or 100%. But this is an oversimplification, since in reality, stiffness doesn't drop uniformly. Some parts of the laminate continue to carry load even after local damage occurs. The authors therefore developed a new degradation model that links stiffness reduction directly to the Tsai-Hill failure factors, allowing the material properties to degrade progressively and realistically based on which part of the material is failing. The model builds on classical lamination theory or CLT, a fundamental approach in composite mechanics that relates the loads and moments acting on a laminate to its in-plane strains and curvature. Using CLT, the researchers could calculate stresses and strains for each layer in the laminate. They also considered thermal stresses, which arise during manufacturing because aluminum and glass epoxy expand differently with temperature. These residual stresses were included in the total stress state, improving the model's accuracy. Another important aspect was the inelastic behavior of aluminum. Instead of assuming aluminum behaves purely elastically, the authors introduced an equivalent elastic modulus that changes after yielding, so the model could capture the metal's plastic deformation. For failure prediction, the Tsai-Hill criteria was applied to the composite layers to check when they start to fail, and the maximum strain criteria was used for the aluminum layers. When failure was detected in a lamina, its stiffness was reduced according to which Tsai-Hill term, longitudinal transverse or shear, contributed the most to failure. If the longitudinal term dominated, it represented fiber failure, signaling ultimate failure of the laminate. If the transverse or shear terms dominated, it represented matrix cracking or fiber matrix debonding. If multiple terms contributed equally, it was treated as total matrix failure, where the layer loses nearly all load carrying capacity. This approach allowed the model to simulate the gradual weakening of the laminate as damage accumulated, a much closer reflection of what happens in real structure. The researchers tested their model on two systems, a pure cross-ply glass epoxy laminate and a full aluminum GFRP fiber metal laminate. For the pure GFRP laminate, the model predicted first ply failure at around 43 megapascal and ultimate failure at 548 megapascal, which matched benchmark experimental data very well. For the fiber metal laminate, which had alternating aluminum and cross-ply glass epoxy layers, the model captured the entire sequence of progressive failures. First, matrix cracking and fiber matrix debonding in the 90-degree layers, followed by fiber failure in the 0-degree layers, and finally yielding and plastic deformation in the aluminum sheets. The predicted stress-strain curves matched experimental results closely for various off-axis loading angles. The model also showed how the dominant failure mode changed with loading direction, fiber failure for smaller angles, and aluminum yielding for larger ones. This ability to track failure progression and stiffness degradation step by step proved that the new model was both accurate and physically meaningful. What makes this work truly important is how it bridges the gap between simplified analytical theories and the complex real behavior of hybrid laminates. It demonstrates that progressive damage modeling can be achieved without using heavy computational tools like final element simulations, just through an improved analytical approach. For engineers, this has huge practical implications. To summarize, Rao and Rao's 2010 study introduced a progressive degradation model based on Tsai-Hill factors that accurately predicts how fiber metal laminates fail under different loading conditions. The model accounts for the nonlinear plasticity of aluminum, the anisotropic behavior of glass epoxy layers, and the interaction between them. Compared with earlier methods, it gives results that are closer to experimental data, while being simpler and computationally efficient. Most importantly, it provides insight into the sequence of damage events, from matrix cracking to final failure, making it practical and reliable tool for mechanical design and failure analysis of hybrid composites. In short, this paper represents an elegant example of how classical mechanics and modern damage modeling can work together to solve real engineering problems, helping us design stronger, safer, and more efficient composite structures for the future. Thank you.